This video is introducing binary search, which is going to be the second search algorithm that we learn in this series. And we're going to see that in some cases, it's more efficient than linear search. So what is binary search? Binary search is an algorithm that has to have a sorted collection of numbers. So with linear search, it was just any list of numbers. With binary search, that list has to be sorted. And the way it's going to do it is we're searching for a particular value. So let's just say k. And if we're looking for k, we're going to look in the middle of that list. And if that middle element is greater than what we're looking for, and we know that the list is sorted, we just have to now start looking to the left of that number to where all the smaller numbers are. And then we find the middle of that group of numbers, and we check to see if the value we're looking for and the value that we're at is greater than or smaller, and we go from there. So basically what we're doing is we're cutting the list in half every time. So we have a whole list, we cut it in half, whatever part doesn't match. So if k is greater than the number, then we know that everything to the left of where we are is too small. So we throw all those numbers away, and now we have a new list that we're looking at. We cut that list in half, right? And then if k is greater at that point, then we throw everything to the right away, and we look at just the left half of numbers. And we keep doing that. We keep cutting the list in half until we either exhaust all possible elements in the list, therefore we say it does not exist, or we find the element we're looking for and we say it does exist. And because we're constantly cutting the number of elements that we have to look at in half, we find that binary search for sorted data is faster than linear search most of the time. Now, let's just walk through an example of this. So we have a list 1, 2, 3, 4, 5, 6, 7, 8, 9, obviously sorted from min to max. And we're looking for the value 8. So we know the value's in here, but let's kind of walk through what we're going to check. Well, we're going to check the middle of the list first, and so that's 5. And we're going to see that 5 is less than 8. So we know that nothing to the left of 5 can be 8 because it is sorted. So now we're going to cut from 5 to 9 in half. And there's not a perfect half in here, so we always kind of take the floor. And so we then go to 7. Now we know that 7 is less than 8, so we know that anything to the left of 7 can't be it. So now we're going to cut this list in half again. So we're cutting 8 and 9 in half. We take the floor so that it puts us at 8. We see that 8 is 8, and therefore we say, hey, we found what we're looking for. Now this is in contrast to linear search, where we start at the beginning element 1 and we work our way all the way through. And so you can see here that there's a lot more steps, a lot more things that we have to do in linear search than we have to do in binary search. So again, binary search is cutting the list in half, and then based on if k is less than or greater than the value that we're currently at, we throw away half the list and then split the new list in half again. And we keep doing this until we either find the element or we've exhausted all possible elements in the list and we return false. Now that we've walked through how binary search is working, let's look at the algorithm itself. So we have the problem statement, which is given a list of numbers, determine if a particular number exists in the list. That's the same problem statement as we have for linear search, right? Because we're just trying to find if a piece of data exists in a collection of data. Now, our inputs are slightly different. Our inputs are an ordered list of n numbers from minimum to maximum. Sometimes you'll see it described as a list in ascending order, right? Something like that. But basically, we know we're sorted from min to max, and we still have that target value. So if we were looking at linear search, the input would have been just a list of n numbers. It didn't have to be ordered or not. And our outputs are the same as we saw in the other search problem, and that's true if k is in L, false otherwise. So what we need to do is we need to kind of keep track of the window of numbers that we need to explore. And when we first start this algorithm, we're looking at the entire list. So the first thing we want to do is set some variable called left to 0 and some variable called right to n minus 1. And what that's doing, it's saying the window that we're searching is the very first element of the list to the very last element of the list. And we always want to check to see if those ever switch. So if our left indice is always greater than or it becomes greater than our right indice, then we know that, oh, we've checked every possible element there is. We can return false. We haven't found it. Okay? So now we need to find the middle element of the left and the right indices that we have. So we just do that by doing floor of the average. Okay, and so now we're going to find that middle location. And now we can check to see if that middle location is less than k. Now, if that middle location is less than k, what does that mean? Think about that for a second. Maybe pause the video and come up with your answer before you resume it. All right, so if that middle element is less than k, then we know k has to be greater, meaning that any value to the left of the middle is going to be too small. So we want to update the new left to be 1 to the right of mid. We don't need to change what the maximum or the right is because k is still might be out there. So we're basically shrinking the array in two, right, in half, by moving left up to mid plus 1. Now we have a new window to search from mid plus 1 to right, which currently right now would be n minus 1. Okay? Once we've updated our new boundary that we're going to be searching, we can then go back up and check to see if those boundaries have flipped, meaning we've finished our search. They haven't. So we then find the new middle element by finding the middle of, again, the new left plus the old right divided by 2, and we get a mid. And now let's say that the middle element is greater than k. So that means that there can be no other values to the right that we want to search, because there's no way that anything greater than mid would equal k, since mid is already greater than k. So we want to bring that right in closer to mid minus 1. And now we have a new search window, our left and our right. And we're going to keep dropping this search window until either right and left have switched, where left is greater than right, therefore we'll return false, we did not find the element, or L at mid is equal to k, therefore we return true because we found the element. So this is how binary search works. And as you can see here, the way I presented this algorithm is different than the way I presented algorithms in previous videos. And you're going to see me try to throw different styles of algorithm presentations out there, just so you can see that there's many ways that you can present algorithms that are still good ways of presenting algorithms. So in the next slide, we're going to kind of take some time to go over this pen and paper and make sure that we truly understand what's going on with binary search. So here on the left, I have the algorithm that we just looked at, and I want to write out a couple of examples to see if I can understand what's going on. So we know that the list has to be sorted. So I'm just going to write a sorted list here. Okay, so the first thing we want to do is set left to be 0. So I'm just going to call it L. We're going to set that to be 0. And we want to set right to be n minus 1. So right, I'll just say R, is going to be 1, 2, 3, 4, 5, 6 minus 1 is 5. And again, these are just the locations within the array. So now we have to ask ourselves, is left greater than right? It's not. So now we need to update what mid might be. And so we simply will take the floor of the left, which is 0, plus the right, which is 5. So that would be 2.5. The floor would be 2. Okay? And I'll just remind everyone that we have our indices here. Okay? So obviously there is no middle element here, a single middle element. But by taking the floor, we know that this is going to be what we consider our middle element. So now we want to check if, oh, I guess we need to pick a value that we're looking for. Let's search for 11. Okay? So let's search to see if we have 11 in the list. So we should return false at some point. So now we will check to see if the middle element is less than k. So is 5 less than k? It is. So now we want left to be updated. So we want left to now become 3. Okay? So basically what we did is we came here, we checked to see if we're greater than or less than. We know that we don't need to search 1 and 3 anymore because k can't be down below 5. So now our new search window is from here to here. Okay? So now we're going to go back to step 2. And we're going to check to see if left is greater than right. Well, 3 is not greater than 5. So now we're going to get a new mid value. And so our new mid value is going to be 5 plus 3, 8, divided by 2, which is 4. And that's the middle value. So now we're going to do that check again. We're going to check to see if 4 is less than k. It is. So we know that we don't need to search anything over here. And our new search window will be here and here. Okay? So now we're going to check to see if left is greater than right. It's not. Well, we have to update our right. I did not, or our left, excuse me. I didn't update our left. So we update it to 5. It's not. They're the same value, so that still won't return false yet. We're going to check to see if 10 is equal to k. It's not. So then when we update again, our left will become 6, and therefore the if left is greater than right condition becomes false, or true, excuse me, and therefore we return false. We couldn't find the element in the list. Good. So now let's do another example where the element is in the list. And I'm just going to do element 3 just so we can see that it works really quick. Left is 0, right is 1, 2, 3, 4, 5 is 4, right? Into C4. So we will then check if the middle element is equal to 3, and if we're searching for 3, we'll see that it is, and we return true. Okay? And so we know that this binary search works. And if you're not still 100% sure, take some time to work through examples like I did here to convince yourself that this algorithm does indeed work. Now, I also want to challenge you with a little mini practice problem here, where I'm going to ask you to pause the video after I give you this question. Once you think about it, then come back and resume the video. So the question I have for you is, given a sorted list, is binary search always faster, or does binary search take fewer steps than linear search? So I'm going to rephrase that one more time. So given a sorted list, does binary search always take fewer steps than linear search? So try to answer that question yourself by pausing the video, work it out, and then come back and we'll review it. Okay, so let's just take this list here as an example. And let's say we're looking for k is equal to 1. How many steps would it take for binary search to find this value? Well, the first thing we have to do is find 3. So we check 3, and it's not that value. So now we're going to split this in half, and we're going to check, well, here we would take the floor, so we're going to check 1, and then we find it. So we see that binary search will take 2 steps. Well, linear search is going to start here, and, well, we found it, we're done. So linear search is only going to take 1 step. Now, of course, this is a very contrived example, but what I'm trying to point out here is that there is not going to be one algorithm that rules them all. When we start talking about complexity analysis, we're going to start talking about best case, worst case, average case. And depending on the application, depending on the data that we're dealing with, we're going to put more emphasis on either the best case, the worst case, or the average case in terms of how do we make a decision of which algorithm or which data structure to use. So hopefully after viewing this video and going through some of the exercises, you have a little bit more understanding of what binary search is. And we're going to use linear search and binary search to start figuring out how do we evaluate these algorithms in terms of their efficiency in the next couple of videos.